So ciao to everyone. I'm Giulia D'Angelo, and today I will bring you into my world, which is visual attention. So what catches your eyes? Why you're looking into specific places and not something else, right? So what's catching your eye? And I do this with Bioinspired and neuromorphic algorithms to model visual attention. So at the moment, as Thiago was saying, I've moved a lot. As you can see, I started my journey in neuromorphic very early at the King's College of London. I was doing predictive coding there with Michael Sprackling. Then I started the PhD in Manchester in collaboration with IIT. In Italy. And then I wrote the Marie Curie with zero chances from my opinion to win it, but I actually got it. And then I moved again here in Prague, and I'm now in Czech Republic, and I am the principal investigator of my project. Let's get in. Okay. Yeah. So that's my dream, and I'm sure it's your dream too, to just keep your meeting, like you're taking your meeting, and then you have a fantastic robot next to you that is preparing a tea and then is cleaning around, right? That's our dream. But all of this needs to be done in a specific way, right? We want an unconstrained environment, right? Because we don't want to constrain the problem. And we want it with low power consumption, right? Because we don't want to recharge the robot every 5 minutes. And then we want very low latency because we need the robot to react very, very, very quickly to things, right? So we want it all, and we are trying to do it with machine learning, deep learning methods. We are trying to tackle the problem in different ways, right? But someone has already done it, right? So if you look, for example, the cat is playing with a toy, right? It's a fairly complex task. Like, would you make a robot to do that? It's not that easy. It's following the toy and it's catching it and it's doing lots of things at the same time, right? Same thing for the dog. Understands that if he gives the paw, it will get something, right? And that's amazing, insanely good how nature has solved this problem. But let's think about humans. I mean, look at the babies interacting with that toy, and it does it effortlessly, right? In this very moment, I'm standing up. I am balancing my weight because I stood up, and I'm talking to you guys, thinking what to say next. Doing all of this in 20 watts, which is insane, right? So it's very easy for me to convince people why I take inspiration from nature saying this, because it just does it better. So there might be something that we need to take inspiration from. Okay, so let's get back to my dream. So I want a cup of tea, and I want also my house to be cleaned, but something is going on here, right? I also want my cat to not burn to hell, right? Because there is a candle that is falling down. Okay, so how do we define attention? What's attention? How do we make the robot prioritize the most important thing in that very moment? Then how do we make the robot, whilst it's doing other things, to say, oh, there's a candle, that's the most important thing, let's look there and let's see what's going on. Now, I'm going to play a video, and I'm super sorry because you can't respond, but I'm going to play the video twice, okay? And just look at the video, and at the end, I will ask you if you caught something. I'm not spoiler anything, and then I will give you the response. Okay, I'm not sure if you caught anything and you can't reply, but two different people. They were two completely different people. Yeah, I can see the faces at least. And why? Because your brain is doing exactly what it should do. You can see that also the t-shirt is different. Your brain is doing exactly what it should do, just getting the most informative information in the scene. Therefore, there was the phone ringing and someone picked the call. That was the most informative information in that scene. And your brain focused on that, right? Disregarding the face recognition and all of the other things. Okay. Someone else had the same idea of looking around and see why we look in specific things into the scene, right? And this someone else is Jarbus. And I call it Jarbus, but I think it's strongly Italian accent. So just look at the name and take the name. So this guy, already in 1967, decided to use an eye tracker and asked to different subjects to look at different situations, different scenarios. And just to let you understand, this is the eye tracker, guys. So this is the monster that he was showing to the subjects. So he was recording eyes movements. So let's have a look here, right? So what we're doing here is moving from one head to another head, right? So what are we doing here? We're basically nosing, like, are they fighting? Are they talking? Are they saying something interesting? Or maybe they're all angry? We're nosing the situation. Here, easy, very easy, triangulation. We are recognizing the face. And here, we do, oh, foliage, nice, oh, bear. And probably we run away, okay? So after years and years and years of studies, Jarbus came out saying, guys, I don't have a clear response. I can tell you that probably what we do is to get the most informative information out from the scene. What this informative information means, still, we don't know. I don't know, and lots of other people don't know. We are trying to tackle this. Okay, so we have the image, then we have the scan path. The scan path is the recording of the eyes moving. And then we have the saliency map, which is the concretization of the fixations over the image. That tells us basically what was interesting for us. For now, I use the word interesting, but now on, I will use the word salient, because interesting implies cognitive biases behind. There's much more. When I say interesting, there's much more. Salient is just where I looked the most. We still need to understand why. Okay, so someone else, and these others, someone else are E.T., Christoph Koch, and Ernest Niebuhr in 1998. They came out saying, okay, let's try as much as we can to model this visual attention, right? And then they tried to understand, okay, what do we do with the visual information that we have? Okay, let's try to extract features, right? Let's try to extract the information of colors, the information of intensity, and the information of orientations, because this might be the basis of what we do, of what we extract from the retina, and so on and so forth. So they extract these features, and then at the very, 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 very end, they combine all of them, and then they sum up all of them, and they say, okay, this was the most salient point because there's more energy there somehow. Fine, this is super cool. But feature extraction is definitely not enough, right? So question is, fine, we have the information of color, intensity, and whatever. How do we perceive items around us? So how do I know that this is a plant and is an entire thingy, right? So we take it for granted. It's hard how we do it. So let's start from here, 1950, okay? I love give some dates so that we understand how hard is this problem. So 1950, Gestalt principles. So in psychology, there is this movement, let's say, Gestaltism. And Gestaltism comes from the word Gestalt. And Gestalt in German means whole, the whole thing, entity, an entire entity. And this Gestalt psychologist came out with some principles on how we understand things in front of us, how we perceptually organize the information. And there it is. We have different rules. These are the rules they came out with, which is closure, similarity, figure ground organization, and proximity. So let's look here. Again, I can't have any response from you, but if I ask you what's here, I'm sure you will say, oh, that's a square. Same thing here, right? That's a dog. You take it for granted again. It's not that easy. Here, triangle, right? Then what we do, what our brain does, is filling these gaps because it's really, really keen on trying to understand what is in front of it. So what we are trying to do is, okay, do I know this thing? Do I know this thing? Let me fill these gaps and see if I can recognize it. And then it comes that it's a square. Same thing here, similarity. If I ask you to group these things in two groups, you will group circle with circles and triangles with triangles. Again, we take it for granted, but that's a perceptual rule. We group for similarity. Same thing here for proximity. We group things that are close to each other. And here we have figure ground organization. So our ability to understand that we have foreground against the background. Okay, so these are the rules that came out from the 1950. Then in 2000, so you can clearly see that the years changed quite a lot. Someone, which is Zhu et al., found in V2 some interesting cells. So just let's have a look at this, right? We have in A and C, the cell is this little thingy, black thingy here. Then we have that if the foreground is on the left of the cell, we have a very good spike activity from these cells. Instead, if the object is on the right, we have some spurious activity, okay? How come? How does the cell know where the object is? Then let's take a closer look at the problem. And let's put the same problem of the square over it, right? Now let's think that that cell has this shape, half moon shape. Now let's think that you have, as it happens often in V1 and V2, different orientation of the same cell. Then if you pull the information from all of these orientations of cells, then you understand why. You understand that the cell is detecting the object. And these are border ownership cells because they give you the ownership of that border. And this is a proto-object. Because it's not an object yet, we might think that is an object. So it's an object to be. And this is how we model these cells. And this is the von Mises filter that is emulating the border ownership cells. Okay, so this is the start of my PhD. I had this model, which is basically the same model that I was talking about before, intensity, color, and orientation. But then what they have done is adding on top this information from the von Mises filter. Therefore, we are not only getting the information of intensity, color, and orientation, but we are also detecting possible objects in the scene. Okay, so imagine I am, I think, 26 years old. I get to IIT, and they give me this model, and I see this creepy guy, and I'm like, okay, fine. What's particular of this robot is that it's neuromorphic. What does that mean? I've done something in London, but what does that mean? So how does a neuromorphic camera work? Fine. Now, let's start from a normal camera. Easy. Every chunk of time, we get the information from each photodiode. easy as it is, right? Then let's imagine I have a bottle. What does happen if the bottle is just stationary on the desk? It happens that I will get the same image over and over because the bottle didn't move, the scenario didn't move, and I will get the same image. So it's kind of useless. But even more, what if the bottle is moving so fast that you completely missed it because it was in between frames? Then let's think differently. Let's not sample the time, but let's sample on the y-axis, which is the luminosity, right? So if you have your photodiodes, and each photodiode is detecting the light. If at the time t0 has some sort of value, let's say 3, and then at the time t1, that value increased to 20 and is over a certain threshold, why not making the photodiode telling us what changed? And this is what happens with the even-based cameras. So what we have is, instead of the sampling in time, we have the sampling on the y-axis. So whenever each photodiode is detecting a difference in light, different from the previous time, then is spiking, is giving us an information. And what happens here is actually I will not get anything when the bottle is stationary because nothing really changed, but I will get lots of spikes if I throw the bottle at you. And how do I get it? Like this, with events. Each photodiode is saying something. The polarity here has changed. Therefore, increment or decrement in light. And then each event, which is each one of this pixel firing somehow, is carrying on the information of the X and Y, position on the grid, the timestamp, so when this happened, and the polarity. So if it was an increment or a decrement in light. And this is what you get with the even-based cameras. So you have the information in time. So now each pixel is asynchronous and is giving you the information in time with the microsecond latency and milliwatts of power consumption, which is really, really, really good. Okay, now we understood what does that mean for the neuromorphic guy. So I had the neuromorphic guy, this attention model, and these are the ingredients, and the neuromorphic cameras into the eyes of ICAP. And I just thought, okay, how can I make ICAP attentive to the scene? How can I make him doing things, reacting to external stimuli, therefore being attentive? And then I thought, okay, I definitely want the intensity because it comes free from the cameras, right? It's just like information of light. Fine, I get that. Then I want that because I want the robot to detect objects that are close to it so that he can interact with it later. Then I want motion. Motion is inherently interesting, right? Because we need to either catch things or avoid things. And this is what I managed to do during my PhD. So these are the 3 channels that I choose for my model. And this is intensity, depth, and motion, exactly as I was saying. In this case of the intensity, we have 2 models. I will tell you later why. But the point is that the depth and the intensity has the von Mises filter because we are detecting objects. The motion does not, because I don't really care to detect if it's an object or not. I just need to detect that there is something, and then I will move either towards it or avoid it, right? So I don't really care to detect if it's an object or not. Okay, so I started with the same model that comes from the RGB model. It's still Bioinspired, but it has this input that is RGB, right? And then what they were doing at the very start, it was, let's do on center surround on and off pathway to detect where I have polarity information, dark over light and light over dark. And then let's do just edge extraction here. And then let's feed it into the model. thing that I had not to do completely because of the event-based cameras, because the event-based cameras are already giving me the information of polarity, and you will get these changes only on the edges of the objects. So I have everything already for free from the camera. And therefore, I created the first model. So split the polarities in two, and I do event frames here. So we collect the events over a period of time, which is in this specific case, 50 to 70 milliseconds. And then we have the two positive and negative frames that they go again, same thing, border ownership pyramid and then grouping pyramid. So we convolve with different orientations of the von Mises filter, and then we sum up here. Okay, so these are the very first results. And we can see that it's running on GPU and is 100 milliseconds. And here we are benchmarking against the RGB model. As you can see here, this is the event based model, and this is the RGB based model. So you can see that we are less spread around, so we are much more localized. And this is also because we did not want to add the center bias. So here they put the center bias for biological reason. We are center biased. And then we are detecting somehow the same saliency map. Here is just to show you that we can detect objects up to 2000 pixels per second. We were just throwing balls at the robot. And here is just to prove that this is the RGB response. This is what catches from the eyes of ICAP, and this is our response. This is just to prove that we can get multiple objects together. And this was interesting. We completely get rid of the clutter. So in the RGB case, you have a very, very bad response here where there's clutter, which is meaningless. In our case, we don't get it. And it's easy, again, because of the events, because here in J, we will have plus, minus, which doesn't let us get a nice response from the convolution with the von Mises filter. Here again, this is clutter. And again, here we can see that there is lots of clutter here, and here we are just looking at the three objects in the scene. Okay, so let's move on to the depth channel. I hope you're still alive. So what we have done here is that we got the stereo events from the cameras, so from the eyes of ICAP, and still event-based. And then here there is a disparity structure. We come from a stereo matching model that again comes from MAR. It's a cooperative stereo matching model. Then we extract the disparity, and this is a disparity map. So the highest the disparity, the closer is that object to the robot. Therefore, the higher the disparity, the higher saliency will get to the closest object directly. So the problem is already solved for the way it's built. And I want to show you how it works from here. Yes, let's build all of this and stay here. Okay, so here you have the RGB video of what's going on. Here you have the stereo events, and here you have the disparity map. Then here you have the model of the intensity, the one that I was just explaining before, right? So this is just intensity fed to the border ownership. Here we have the depth fed into the border ownership, so our disparity map. Let's see what's going on. So when there is one object, fine, the most salient point, the red one, is on the bottle, fine. What happens if I put another object? It's pinpoint here. This is not true here because it's just focused on the closest object. And of course, even if I change the two objects, okay? Now, we have done different experiments. I don't want to bother you too much, but here is basically trying to respond to, of course, reviewer 2 telling us, well, but yeah, you can do the same thing, just doing the disparity map. Sure. But the things that comes from the disparity map are also not objects, right? So look at the difference between the disparity map here and the attention here is on my arms, because I was doing Karate Kid in front of the robot. And the attention is on my arms, where it should be. Instead here, a disparity map will give you just the disparity, right? So not the same thing. And we proved it repetitively. Then here we have the comparison against the ground truth. Here we should open another chapter and blah, blah, blah. But the point is, this is the depth, this is the RGB saliency map, and this is our response, okay? So the even-based proto saliency map with the depth. We compete against 3D fixations, which are subject fixations, real humans fixating at things. And a stupid bottom-up model can never compete with humans. So this is an evaluation on how good we are with respect to the fixations, but we can't really see that this is a real benchmark, because our model, of course, does not imply all of the things that humans can do. And this explains our results that are not one for the case of the structural similarity, which is the best metric for us, because each of this metric will perform differently depending on the data set. So in our case, the structural similarity, it's the best one, and it's still not giving us something out or over 0.6. And here is the comparison between our model and the RGB one. We are much more precise than them. Just to be noticed that now is 170 milliseconds on a GPU, because we need to extract the disparity and then we do the attention. Okay, so I told you that I had 2 models here, right? So was I satisfied using given frame? Not at all, because I don't like frames. And in my research, I'm trying to get away as much as I can to even frames, but I want to use the events as stream of information. Then what I have done is, okay, let's use Spinnaker and let's make it end-to-end neuromorphic from the information of the events, which is completely asynchronous, to the computation through a neuromorphic platform. Then the question here is, again, how does a neuromorphic platform work? What's the point? What does it do? And then if you think of a GPU, it's very easy, right? You compute a thing here in the central processing unit, and then you put 2 plus 2, and you put the 4 in the memory. And then you need to do plus 3. And then you go back to the memory, you take the 4, you bring it back to the CPU, you do the plus 3, and then again, boom, the 7, you put it here in the memory, right? Is this efficient? No, not that much, because I need to move. But then, is there anything that we know that is computing and storing the memory in the same place? Yes, and it's a neuron. A neuron is depolarizing, so it will have some sort of current coming from ions with sodium and calcium. They enter the cell, and then the membrane potential is changing. So what it does is a depolarization, and then it goes over a certain threshold, and it creates what we call spike, and it repolarizes, right? But if you think a little bit about what it's doing, is integrating in time, so it's computing, but this compute depends on what happened before. So this is co-localization of computing and memory. So this is the very first idea. And then a spike is nothing else more than 0 and 1. So it's really, really let's say you can read it as digital, and then you can translate it for everything else we do. So there are different kind of neuromorphic platforms, and the beauty of it is, like, for example, this is Spinnaker, this is an event-based cameras, forget about that, this is Dynaps, this is the SPEC. The SPEC is a DVS sensor integrated directly with the Dynaps CNN, and here you do spiking convolutional neural network, and this is UIHI. So the point is that this is going to be a very single mini unit of a population. So you have a population of neurons, and in this chip, which Spinnaker has, the Spinnaker 5 has 48 chips. In every chip, which is based ARM cores, you can reproduce 256 neurons. So this makes the board to handle 70K neurons overall. And then what you can do is connections, inhibitions, and excitations amongst your neurons, right? So here, in this case, we are emulating digitally the behavior of a neuron. In this very case here, the analog one, we are emulating on hardware what's going on. And this is just to show that, of course, gives you a little bit more freedom with respect to GPUs, because GPUs don't talk to each other, they don't do connections among each other, they don't do excitation and inhibitions among each other. These two things are two separate things. They're two different ways of computing. And I know everyone loves benchmark, but the benchmark needs to be done very well if you want to compare these two guys, because these two guys do two complete different things. So, for example, one really important thing that we need to say here, not so much in terms of latency, because now crazy GPUs can have a very good latency, but look at the power consumption and look at our power consumption, right? That's the point. Okay, let's go back there and let's look at the fully neuromorphic end-to-end proto-object model. So we have our Vomises filter that is repeated over and over. Therefore, it's a spiking convolutional neural network. You don't have the kernel that is convolving, but you just replace the kernel many, many times all over the visual field, and then you do a math multiplication, math. Then what happens is, if you connect these two guys opposite direction to a filter neuron and then to a proto-object neuron, this means that if I have the two facing towards each other, I need to spike because there might be something that is enclosed there. And then I have different sizes, so also scale invariant. And this is our response. I mean, if you compare it to the event-driven proto-object one, the very first one, the intensity, and then you compare it to the 3D, so the depth proto-object, we are much more precise because of the nature of the spikes. But the really cool thing is this. We got to run everything in 16 milliseconds, which is insane, right? If it's compared to the GPUs. Then we have done again the benchmark against the subjects, and again, same kind of values. These are the latency. But then, of course, it's not everything good, because to do this, to model the full network, we needed 6 Spinnaker boards. Okay, so the scalability in neuromorphic is a known problem. We need to scale. We need the boards to have many neurons. Okay. Then we have the motion channel. The motion channel is the last one, but is actually the first one that I have done in my PhD, which is very, very, very easy. This is done again in Spinnaker. And then just imagine that this is a visual field, okay? Forget about how weird the receptive fields are. I will tell you in a second. The most important thing here is, if I have this downsampling, non-uniform downsampling, and then I have this area here, the green one, that is triggered before the blue one, that's a left to right motion. So if you connect thoroughly your neurons, you will have a left to right to left, top to bottom, and bottom to top neurons to decode your directions of the objects in the visual field in 4 milliseconds, which is super impressive, because we are just waiting for the internal clock of Spinnaker. It still has a clock because it's digital, and it has 1 millisecond for each of these directions layer. So here we just show that the model is responding correctly to the preferred direction. So the left to right is responding correctly to the left to right motion. And here is to prove, again, reviewer 2. But can you get also the transversal directions? Sure, yes. And then with the combination of right to left and top to bottom and whatever, you also get the information of transversal movements. And here is just to tell you that something particular. So I told you this is non-uniform downsampling. Why? Because I'm trying to reproduce what's happening in the retina. In the retina, we have the fovea that is highly resoluted. In the periphery, we have receptive fields that are way bigger. Because again, we do not fixate with our periphery. We foveate there, and it's called foveating there because of the fovea. We move the fovea towards the things that are our interest. Why? Because we have more resolution, and then we can recognize better. So for the way this is done, there is a delay between these two neurons. Therefore, the bigger the size of the receptive field, the higher the speed to detect the object that is moving over these two receptive fields, because there's literally more pixels to get across in order to trigger them. And then at the end, what happened is that I decode a very fast speed in the periphery and a very low speed in the center, which is exactly what happens to us as humans. We detect very fast things just in the periphery, again, because we need to foveate there. So we catch it first here, and then we foveate then, and we can understand with our resolution what's going on. And this is shown here. So this is the comparison between the uniform downsampling and the centric downsampling. Because what I'm telling you here is that I have a range of speed, and I need way less mean firing rate to detect the same speed, because only the receptive fields that are selective to that speed will be triggered. In the case of the uniform, they will all be triggered. Okay, so we've made it, guys. This is the end of my PhD. And then at the end of my PhD, I had this amazing model. So, wow, yes, I can detect the saliency map in any way. Ask me which kind of saliency map do you want. But then, is there any saliency map in the brain? That's the question that I'm asking myself now. Have I done all of this work for a reason or not? So let's think for a second here why I don't like frames. And you can have your own opinion, but I will convince you. So look at this. What we think is that we have a frame of a bee reproduced here into the retina and somehow reproduced here into the cortex. So we do think that we have frames. That's not the case, because if you look very, very thoroughly in one point into the scene, and something is going on at a distance from the center, from where you're looking, you don't catch it. Therefore, if you think that we have frames, we should be able to do subtraction of the frame and catch everything that is going on, but it's not true. We see where we focus. We highly resoluted see only where we focus. So we don't have frames in time that are, just centered into the cortex as it is. This is what we do. What we do is constant stream of events and information and spikes into the cortex. And most importantly, we are following this thingy here. So I was like, is it the active interaction with the word, which is actually the response of what I'm looking for? I don't think I want frames, but I just want to play with what we do with our eyes over the scene. Therefore, I need to look for embodiment, which is a very buzzword now. Everyone is doing embodiment. And there is a nice paper that came out saying, oh, we have the same model that is running on 100,000 different robots, and this is embodied. That's the opposite of embodying, because embodiment means that you cannot disassociate the mind and the body. I perceive the word as I perceive it because of my hands, because of how my hands are. And if I had 3 fingers, I would be perceiving the word differently. If I had a different sensor distribution on my fingers, I would be perceiving the word even more differently, right? So if you change the body of a robot, therefore, you need to change also the algorithm BI, because mind and body are connected. And that's the point of embodiment. Therefore, I tried to understand a little bit more, and it came out that if this is the standard view, this happens to be the sensory motor view. And when I read this the first time, I was like, oh wow, this makes lots of sense. But what does this mean? Sensory motor, it means that we need to connect what you do, so moving the eyes, to the sensory changes that happened, because you moving your eyes will change the visual input that you will store afterwards. But that depends on you moving. So this sensory motor contingency is linking the action with the visual change, the action with the changes more in general. So I was thinking, okay, well, but if I have my visual attention, right, and I focus on this part of the cup, and I start moving around, right? And what I do is the association of what I see, so this little rise, and the joints pan and tilt of my eyes. Isn't it true that this will create a different sequence of actions and visual changes? And this might classify that a cup is a cup and a book is a book. Therefore, I do not need to train a model for a month with 100,000 data to teach that a cup is a cup, because the shape matter and the shape is enough, and the movement of my eyes over the object will help me. And therefore, perception is not an isolated processing step, but is searches for relationship between actions and the changes that comes after these actions. And this is the project that I came out with for the Marie Curie, which is basically what I've just said, right? I have the pan and tilt movement for ICAP, because of course it followed me here in Prague. So I have the creepy guy with me here, and then it will move pan and tilt with the eyes, and it will also might move the wrist movements. Why? Because if you look at babies, what they do is this. They have an object. When they need to learn a new object, they have an object. They scan the object with their eyes and they move it, right? Because you have more points of view, because you remove the occlusion problem. This is how they train themselves to understand the new object. Then, of course, needs to have some parent telling the cup is the cup. So there is some supervision there. But that's the visual point. So here we will have some sensory observation, and we will move because of the attention. So I will move depending on where is the salient point, and then there is the motion, right? So I have my joints, and this is, again, another part of the sensory. So I'm still getting the information from the event-based cameras, and this is the creepy guy. I will do this in frame-based, event-based, and on SNN. And my hope is to benchmark everything. Don't know, I will probably die before doing it. Okay, so I don't work only in attention. I do other things too. It seems unbelievable. But I do it with the same filter. So this filter is actually very cool because it allows you to do lots of things. And for example, if you look at this banana shape, it's kind of the shape of the coastline. So there was a guy that one time saw me when I was doing a talk for Open Neuromorphic, and he was like, oh, look, I'm doing shoreline monitoring. We could use your attention. And I was like, nah, no, my attention is not going to work. Let's try differently. And this is how we have done it. We are just using one specific orientation of the von Mises filter with slightly different. So 0, 15, and minus 15, but definitely not this, because this is an object and the coastline is much more aligned, right? And then this is the spiking model, and this is how it performs. So you have here the RGB, the event-driven data, and then you have the monopolarity, the ground truth and the detection, and here you have the model spiking where the coastline is. Very easy. I mean, easy. Why I go around saying that my work is easy? But the point is that why do we do crazy learning when this is already working like this? And the point is also that I'm doing this in 20 milliseconds with 0.3 milliwatts, and there's no training at all. So we could actually use the learning for more interesting and complex tasks rather than learning optic flow, right? This is just another work. I just put a feedback from the border ownership to the grouping just to understand if I can enhance more and more and more that there is an object so much that then I segment. And this is our segmentation and is in peer review, and God forbid when this will be out because it's 2 years now. Then I went to Telluride, which I strongly encourage everyone. We just came out with the topic proposal on LinkedIn. It's a beautiful workshop. It's actually the neuromorphic workshop. It's really the first neuromorphic workshop that ever came from Misha Mahowald and Toby Delbrook and all of the people that were there at the very start of this field. And then basically there was this guy, we were in Toby's place, Toby Delbrook's place, and he was like, I have a robot. And I was like, I have attention. And then we made the robot wandering around because of attention. Then this is the last thing I'm working on, and I'm trying to suppress the events because of course you have events every time you move your camera, you have events, and then you don't distinguish anymore what's an object moving or you moving the camera. So I'm visually enhancing object motion sensitivity, and then I put the attention on top of it just to catch if what's moving against the motion of the camera is an object or not, and then I feed this into an angle SNN control. And I'm doing this with lots of friends, nice friends, and the Nengo part is done from Michael Furlong. And then I'm doing this part with Vittoria Clerico, and then with Alex Adivjanov, which is with me every time, every day, doing lots of other things. And then in this case, what I want to say is that I also closed the loop, which is interesting. And this model is adaptable by nature. I don't need to retrain anything. And this is the end. These are the people I collaborate most, which is Yulia Sandamiskaya, Dylan Moore from Simpsons, Chiara Bartolozzi, of course, she was my supervisor during my PhD. This is Alexander Adijanov. This is the professor here in Prague, which is strong in embodiment, is teaching me the embodiment part. And this is the very Ernest Niebuhr of the very first attention model from 1998. And I have the pleasure to work with him. And guys, I have a podcast, and just listen to it, please. It's super cool. And I'm doing it with Sunny Baines from the University College London and Ralph Etienne Cummings, which is actually the guy of the proto-object model from 2014. And he's at the Johns Hopkins University. And here you have lots of people talking about neuromorphic, and not just random people, but the best people that you can find in neuromorphic. I am the editor of Neuropack, Open Neuromorphic, and from this year, I'm the communication chair from Telluride Neuromorphic Workshop. And this is just a spoiler that something will come out soon from me and Fabrizio Tatti, and it might be another very cool video recorded now podcast. And thank you so much.